The last topic in our equilibrium unit is the equilibrium of slightly soluble salts. Now, when we say slightly soluble salts, what we mean is, pardon me, salts refer to ionic compounds. Okay, and when we say slightly soluble, this means things that are mostly insoluble. Okay, so in grade 11, you would have learned about your solubility rules, and there are certain compounds that we know are almost completely insoluble in water. Things like silver chloride, lead iodide, lots of those types of ionic compounds. But there's always a little tiny bit that can dissolve. So, a few key terms. Okay, the solubility product constant is when we calculate the K value for a slightly soluble salt. Okay, and we call it KSP, where the SP stands for solubility product. Okay, and it's determined the same way that you would any other K value, products over reactants, and we include only aqueous substances. And it's always calculated for when a solution is perfectly saturated. So the K value tells us basically how much of the solid can be dissolved in water at a specific temperature. Molar solubility, okay, is similar, but it's specifically measured in moles per liter. So we know that K has no units. Okay, it's a ratio of products to reactants, but molar solubility is measured in moles per liter, and it tells us the solubility in moles of how much a solute can dissolve in 1 liter of water to form a saturated solution. And the last term is solubility, so not molar solubility, just like plain regular solubility, which is measured in grams per liter instead of moles per liter. So molar solubility is moles per liter, okay? And if it just says solubility, then grams per liter, okay? Which we can determine, okay, using the molar mass of the compound, okay, to get from moles to grams. So those are sort of 3 terms that you should know the difference between and how to calculate them, or if they're given to you, we'll do some example questions of that. So a slightly soluble salt, we're going to look at the example silver chloride. Okay, here we've got solid silver chloride, and a very small amount of it will be able to dissociate or dissolve in water, okay, to form ions, silver ions and chloride ions. When we determine the KSP expression for a slightly soluble salt, okay, it's still products over reactants, but in this case, our reactants for slightly soluble salts are always going to be solids, okay, because this is the dissolution reaction, okay, of that particular solid. So because it's a solid, okay, we don't include it in our KSP expression, so there's nothing like underneath, okay, there's no denominator, it's just over like 1, so we don't need to write anything. Okay, so we're just going to have our products, okay, written in as ions. You should include the charge of the ions, okay, and that would be our KSP expression, or the formula for how we would determine KSP. If you're looking at a reaction that has coefficients, so in this particular one, there's coefficients of only 1, so it's the same, just 1 and 1 there. But if you were looking at a different reaction where you had coefficients in front of your ions, okay, they are still going to become exponents, just like we've seen in other equilibrium expressions, okay, where the 2 becomes a squared, okay, for that example. And again, this one, there's a solid, so there's no denominator there. We just take our products, okay, and that gives us our KSP expression. The KSP for a bunch of known solids can be found in your textbook. Okay, so here you can kind of highlight that section is where the list of slightly soluble salts and their KSP values is in your textbook. So some questions you'll have to check that table and use the KSP that's given there to answer a question. And sometimes the KSP will be given to you in the question. So on a test situation, if you needed the KSP, I would just give it to you because you won't have access to your textbook in a test. So let's do a few practice questions. Okay, they work kind of the same way as the other equilibrium questions have, but they look a little bit different in the setup of the reaction because we're looking at dissolution reactions, not a reaction where you're actually having like a chemical change. It's more of a physical change as we go from solid to aqueous. So first type that we can look at, okay, is finding KSP. So in this question, we're going to be finding the KSP value. We're looking at, if you want to follow along in your textbook, page 546. We're going to do silver carbonate. So the molar solubility, which remember is in moles per liter, of silver carbonate, so Ag2CO3, is 1.3 times 10 to the negative 4 moles per liter. Okay, and remember that these are slightly soluble salts, which means all of their molar solubilities are going to be really small numbers. If you ever get a molar solubility or a K value that's really big, then you've done something wrong. You've made some kind of error, okay? Your molar solubility should always be really small numbers for these types of questions because we're only looking at things that only dissolve a small amount. Okay, so we're going to be finding the KSP. Our reaction here, okay, is looking at the dissolution of silver carbonate. So there's our solid. Okay, and a very small amount of it is going to dissociate. We want to make sure our equation is balanced. So 2 Ag plus and 1 CO3, 2 minus. And these are both aqueous. So to determine the KSP, okay, products over reactants, okay, again, our solid is not going to be included. So we've got the concentration of Ag plus squared times the concentration of CO3, 2 minus. Now, to figure out what these concentrations are, we're going to be using that molar solubility, okay, that tells us how much of it can actually dissolve in water. But we need to take into account the fact that there's a mole ratio of 1 to 2 to 1 there. So when we are trying to figure this out, I'll use a different color here. Okay. The concentration of Ag plus is going to be equal to 2 times the molar solubility of Ag2CO3. Okay, and for the CO3 2 minus, it will just be equal to 1. Okay, it's a 1-to-1 mole ratio for the carbonate and the silver carbonate. Okay, 1-to-1. So those are going to be equal. But for the silver, okay, here we've got silver to carbonate. It's a 2-to-1 ratio, which is why we add this 2 out in front here. Okay, so that way we can figure out what it is we're using. There's our molar solubility, so we're going to sub that in. Okay, KSP is equal to 2 times 1.3 times 10 to the negative 4 squared times 1.3 times 10 to the negative 4. Okay, so I'm putting that number in for those. Solving here, KSP will then be equal to 8.8 times 10 to the negative 12. Okay, and there's no unit on that, and we're keeping 2 significant figures. Okay, so we can say, therefore, the KSP of silver carbonate is 8.8 times 10 to the power of negative 12. Okay, so we can find KSP that way if and only if we're given molar solubility. So this is KSP from molar solubility. Sometimes you won't have that information given to you, in which case you might need to use like an ice table or something. We're going to do an example of something like that. So next question, number 2. The second type of question we can have here is calculating molar solubility from KSP. So it's kind of the reverse. So you'd be given the KSP either in the question or from the textbook, okay, from that table on page, it was 545 there. Okay, and we can find the concentration, okay, molar solubility is the concentration in moles per liter, okay, of the ions, okay, that would be dissolving in water. So for this reaction, we're going to look at barium fluoride. So our reaction here is BaF2 solid will form barium ion, aqueous, and 2 fluorine ions when it dissociates in water. Okay, the KSP for this reaction or this dissolution is 1.7 times 10 to the negative 6. So for this question, we are going to need an ice table. Okay, this is very similar to finding concentrations at equilibrium of a regular KEQ question. The only difference is that because our reactant is a solid, we're basically not going to be including that in our ice table or our calculations because of it being a solid. So it's actually a little bit easier to solve than the other questions that are like this for just a regular equilibrium question. So we're going to make an ice table with our KSP, we know, is going to be equal to Ba2 plus times the concentration of F minus squared, right? That is our KSP expression. We know what our KSP value is, but we don't know what those concentrations are. So our ice table, here we've got Ba2 plus and F minus. Okay, so there's basically just no reactants. If you want to put the reactants in, you can, but you're basically just going to be crossing it out anyway because it doesn't apply when it's a pure solid. So here, initial change and equilibrium, okay, initial is 0. We've got plus x and plus 2x, okay, the 2 there is from the 2 in the equation. So we know that this is going to be x at equilibrium, this is going to be 2x at equilibrium. So we can take those and we can sub them in to our KSP expression and solve for x to determine those concentrations. So now I'm going to put my KSP values in and solve for x. So I've got 1.7 times 10 to the power of negative 6 equal to x times 2x squared. Remember that squared needs to be on the outside of the brackets, okay, because it's going to apply to everything inside the brackets, not just the x. So now we're solving for x. 1.7 times 10 to the negative 6 is equal to, I'm putting that in, so that's going to be x times 4x squared. Okay, that itself is going to give me 4x to the power of 3. So just to save space, I'm going to switch right over to that. Okay, 4x to the power of 3. I'm going to divide both sides by 4. And then I'm going to take the cubed root. So dividing by 4. And then cube root of that. Okay, that's going to cancel out the 3's. 4's get canceled. I'm going to be left with x equal to 7.5 times 10 to the negative 3 moles per liter. Remember, x is always concentration in moles per liter. Okay, and this, okay, is basically equal to that, which is also equal to the molar solubility of of the salt. So we're going to finish this off with a therefore statement. Therefore, the molar solubility of barium fluoride is 7.5 times 10 to the power of negative 3 moles per liter. Okay, so this is just like finding a concentration at equilibrium with an ice table, like the ones we've done before. We're just calling, we have slightly different language when we're looking at solubility, KSP questions, rather than equilibrium of reaction questions. Okay, we have one more question example to go through. So I'm gonna move this along a little bit. The last type of question is looking at predicting whether a precipitate is going to form, okay, based on a certain amount of solid that's added to a certain volume of liquid, okay, and knowing whether, okay, is it all going to dissolve, okay, or is it going to form a precipitate, okay? So the way that we solve these is very similar to the questions that we did with Q and K. So this time we're calculating QSP and we're going to compare it to the KSP and see which one is bigger to know whether a precipitate forms or does not form. Okay, so we're doing the example from page 548 if you want to follow along in your textbook. The reaction that we're looking at is barium chloride. So I'm going to write out the overall reaction here. We're adding barium chloride, aqueous, plus potassium sulfate, which is also aqueous, to form 2KCl aqueous. This is a double displacement reaction, and barium sulfate, which is a solid. Okay, so this barium sulfate is the slightly soluble salt we're going to be looking at. So we want to know, based on the amounts of our reactants, okay, are we going to see a precipitate form? So in the question, it gives us the concentrations and volumes of the two reactants. So barium chloride, okay, we're starting with our concentration of 0.0040 moles per liter. And our volume that we're starting off with is 200 milliliters. We're also given the amount and concentration of the potassium sulfate. So concentration of that we're putting in is 0.0080 moles per liter. And our volume is 600 milliliters. So to help you through questions like this, I find it really helpful to think of the actual reaction in terms of like you've got a beaker and you're pouring two liquids together and then what are you making? So if this is our beaker, okay, let's say that's our beaker. What we're going to put into here is 200 mils, okay, of the barium chloride. And we're putting in 600 mils of the potassium sulfate. So we're mixing all of those together. And that's going to give us a total volume equal to 800 milliliters. So we pour in one, we pour in the other, we kind of mix them together. Okay, and we're going to have this big soup of ions, and we're going to see, is a precipitate going to form or not? Okay, we need this total volume at the end, okay, because we're going to be using the dilution equation, C1V1 equals C2V2, to determine the concentration of the ions, okay, that are making up this barium sulfate to see if they'll be soluble or not. Okay, so the solubility reaction, okay, of barium sulfate that we're looking at, okay, is we've got BaSO4 solid. We want to know how much of it is actually going to be able to dissolve. So how much is going to break into ions? So we're going to write out the dissolution equation. There. Okay, in the end, this is actually what we're going to be looking for. Okay, the KSP for this reaction, okay, this dissolution, is 1.08 times 10 to the power of negative 10. Now that number you would have to look up in that table in your textbook, or in some cases that will be given to you in the question. So we're going to see if, based on what we've got, we're going to calculate a QSP, and then we're going to compare it to this KSP and see if it's all going to dissolve or not. So first thing we need to do is determine the concentration of the ions. Okay, so let's find the concentration of Ba2 plus first. Okay, so we're going to do that ion first. Concentration of this is going to be equal to C2. That's what we're going to be trying to find. And we're going to use C1V1 equals C2V2, the dilution equation, to figure out what that is. Okay, the concentration originally, C1, okay, is this one, C1, was that 0.0040 moles per liter. V1, the original volume, was 200 milliliters. And V2 is the volume, the total volume at the end, which is that 800 milliliters. Now, because these volumes are both in milliliters, we can leave them in milliliters. We don't need to convert them into liters, but you can if you want to. So C1V1 equals C2V2. We rearrange, okay, to solve for C2. We can put all of our numbers in. So C1, 0.004 times 200 divided by 800 gives me C2, which is going to be equal to 1.0 times 10 to the negative 3 moles per liter. Okay, so that's the concentration of our barium ion. So I'm going to kind of highlight this one in blue. I don't have a ton of space on this paper, so it's going to get a little bit messy, so I'm sorry about that. Okay, we'll do the other one in, let's do black. We haven't had black yet. Try and kind of keep things separate. We're going to calculate the concentration of the sulfate ions next. Okay, so again, this is going to be equal to C2, and this time we're going to use the data from our potassium sulfate. So that's going to be C1 is 0.0080 moles per liter. V1 is equal to 600 milliliters of that solution. V2, our total final volume, is 800 milliliters. Okay, so we're going to find C2. C2 is equal to, again, we're using the same equation. So C1, 0.008 times V1, 600 divided by V2 is 800. So that's going to give me C2 is equal to 6.0 times 10 to the negative 3 moles per liter. Okay, now that I have those two concentrations, okay, so this was for that one, I can now find QSP. So QSP is just like finding Q before, so it's the same expression or formula as the KSP, but we're just not necessarily using the molar solubility concentrations. We're using whatever concentrations we've got. So we've got concentrations there and there. So I've got the concentration of barium times the concentration of SO42 minus sulfate. I'm going to put those numbers in. Barium was 1.0 times 10 to the negative 3 moles per liter times 6.0 times 10 to the negative 3 moles per liter. Gives us a QSP of 6.0 times 10 to the negative 6. So here we're going to see that QSP is greater than the KSP. So KSP again is this number here. Okay, so that 6 is greater than the 1.8 times 10 to the negative 10. And if there's more available than there is that can be dissolved, so a larger Q than a K, okay, then that means that yes, a precipitate will form. Okay, so in general, just kind of make this as a little note down here. Okay, if QSP is greater than KSP, a precipitate is going to form. If QSP is less than KSP, then you're going to have no precipitate forming. And if QSP is equal to KSP, then you have a perfectly saturated solution. Oops. Saturated solution. So we'll look at a few of these practice questions in class, but that's it for now. Have a good night.